Now, we just covered how we could systematically or algorithmically construct a basis for each of the 4 fundamental subspaces of any matrix. But I also want to look at other situations where maybe we have different, maybe more interesting or more fun constructions. So let's think about a situation where we're studying the incidence matrix of a directed graph. Here, I want to look at the null space of that matrix. And there's a really cool result which connects the idea of the null space of our incidence matrix to this concept of circuit rank. So remember, one of the things we said about the incidence matrix of a directed graph is that if you look at any path vector that represents a cycle, that path vector is in the null space. So it turns out that we can construct a basis for the null space by sort of systematically figuring out like the structure of the cycles within the digraph. So here's what the theorem says. Let's purge the minimum number of arrows necessary to break all the cycles in a directed graph. Remember, the number of arrows necessary to purge, or the minimum number of arrows necessary to break all cycles is the circuit rank. So here, I'm choosing to purge A2 and A4. And by purge, I just mean if I remove those 2 vectors, I would break all the cycles. And it does take me 2 to break all cycles. So I'm removing them from the directed graph. Now, I'm removing them in my head, but I'm still thinking of them as being represented in the directed graph. Now, here's what we do. For each one of those vectors we just removed, let's think of a cycle that would have passed through exactly one of those vectors. So here we just purged 2 arrows. So let's think of a cycle that would have passed through one of those vectors. So here is a cycle vector that passes through the arrow A2 that we just dropped exactly once. So this is the cycle that goes through A2, then through A3, and then against A1. Numerically, we represent that cycle with the vector -1, 1, 1, 0, 0. So that's one vector. But remember, we purged 2 vectors. So let's look at the second vector we purged, which was the second arrow we purged, which was the arrow A4. And that arrow connected V2 to V1. And here what we're looking at is a cycle that passes through A4 exactly once while avoiding the other purged vector. So here, the cycle I'm choosing goes through A4 and then through A1. And numerically, we can represent this cycle with the cycle vector 1, 0, 0, 1, 0. So what we're suggesting is a systematic procedure. Purge the minimum number of arrows necessary to break the cycles. Go back to the original digraph and look at each of those arrows. Look at one cycle that goes through that arrow once and avoids the other purged arrows, and represent that cycle numerically with cycle vectors. If you go through this procedure, you will always produce a basis of the null space of the matrix. So the 2 vectors that we just constructed here form a basis for the null space of our incidence matrix. The cool thing about this process is that we don't even need to write down the incidence matrix to find this basis, which is kind of fun because, like, if you didn't know what if you were in a different context and someone just hands you a matrix and asks you to find a basis of the null space, the procedure we just went through in the previous video said we would have to row reduce the matrix and then write all solutions to AV equals 0 as a linear combination of the pivot solutions. Here, we can take advantage of the geometry of the directed graph, and namely, we can study the cycles in a systematic way to construct a basis of the null space of our matrix. So in this particular example, the null space of our incidence matrix is the span of the 2 vectors that we just constructed. Okay, cool. So that's the null space. What about the left null space? So the left null space, remember, is the null space of the transpose. It turns out that the null space of the transpose is connected to the idea of connected components. So let's say we're studying a directed graph, and let's label each connected component G1, G2 up to GK. So this directed graph has 2 connected components, G1 and G2. Here's what we're going to do. We're going to look at what's called the classification vectors of these connected components. What is a classification vector? It's a vector that tells you which node lives in which connected component. So here we have two connected components, so we'll have two classification vectors. So the first one is v sub g1, and this is a vector that's indexed by the nodes in the directed graph. And what we do is we pick up a 1 if the node lives in the first connected component, and we pick up a 0 otherwise. So here, the first connected component is home to the nodes v1, v2, and v3. So the vector we're interested in here is 1, 1, 1, 0, 0. So the first connected component is home to the first three nodes. So we put 1s in those positions and 0s everywhere else. We have two connected components though, so we need a second classification vector. This classification vector will indicate the information that the second two nodes lived in the second connected component. So we'll get 1s in the 4, 5 positions and 0s in the other positions. And that's because the fourth and fifth nodes live in the second connected component, and the other nodes do not live in that connected component. So this procedure is actually simpler than the procedure for constructing a basis for the null space, because all we have to do is figure out which nodes live in which connected component. And it turns out that these classification vectors always form a basis of the null space of the transpose of our incidence matrix. In other words, the left null space. So in the example we've just constructed here, the left null space of our incidence matrix is spanned by these two vectors. So, and these two vectors give a basis. Again, the beauty of the theory here is that we don't even need to look at the original incidence matrix to construct a basis for the left null space.